In this lecture, we're just going to finish up Chapter 5 by going over a whole bunch of examples to give you exposure to different situations. All right, so let's start with our first one. So the figure shows that a block, S, which is the sliding block, with mass m is equal to 3.3 kilograms. The block is free to move along a horizontal frictionless surface and connected by a cord that wraps over a frictionless pulley to a second block, H, which is our hanging block, with mass of 2.1 kilograms. The cord and pulley have negligible mass compared to the blocks. They are massless. The hanging block H falls as the sliding block S accelerates to the right. All right, so our hanging block is going to be pulling down, which is going to cause our block up here to slide over to the right. And since there's no friction, there's nothing impeding the block up here from doing that. All right, so find A, the acceleration of block S, and the acceleration of block H, and then also the tension in the cord. All right, so things that we need to consider. Well, forces, masses, and accelerations are involved. Therefore, we need to use Newton's second law. And this equation here is pretty much what we're going to use for all problems dealing with force, at least eventually. The expression F is equal to ma is a vector equation. So we can write it as a three-component equation. Right? So we can write it in the x direction, y direction, and z direction. Now in this case, we have things happening in the x and the y direction, so those are the two that are going to be important to us. We need to identify the forces acting on each of the bodies and draw the free body diagram. So that's what we have down over here. You see that with our sliding block, which is this one over here, which is has a mass of big M, we're going to have the force of gravity pulling down. We have the normal force going up. Those two are going to cancel each other out because there's no motion in that direction. And then they have a tension to the right. Now the other block is just going to have the force of gravity going down and the tension going up with the acceleration going down. All right, so this acceleration is the same as this acceleration. Right, they're going to be the same acceleration because they're both moving as one. Also, this tension is going to be the same as this tension because it's one string. So anytime you have one string, even if it's attached by or is touching a pulley here that changes the direction of the tension, it's one string, so it's going to have the same tension. That's something important we need to remember. Okay. All right, so continuing on. So from the free body diagrams, we write Newton's second law in vector form, assuming a direction of acceleration for the whole system. So we're going to assume the acceleration is to the right and down, as shown here in our free body diagrams. Now identify the net forces for the sliding and the hanging block. So we need to look at the net forces in the x direction and the net forces in the y direction. All right, so for the sliding block, which does not accelerate vertically, so we're going to look at each block separately. You have our net in the y direction is just going to, or is equal to big mass times the acceleration in the y direction. All right, well, like we said, there's no acceleration in the y direction for this mass. So the acceleration, or the right side of the equation, is going to equal 0. So you sum all the forces together, you just have the normal force going up and the force of gravity going down. So we put a negative sign in front of the force of gravity because it's going down. Set that equal to 0. And then through that equation, we see that the normal force is just going to be equal to the force of gravity. Right, and this is just mg. Also, for S, in the x direction, there's only one force component, which is T. All right, so now if we're looking again at the big block that's sitting on the table or on the box, we're going to look at the x direction, and the only force that we have is T. So we set that equal to the m, or big M, times the acceleration. The acceleration is just going to be A, which is what we said over here, and then that's going to be equal to the tension because that's the only force. All right, so for the hanging block, because the acceleration is along the y-axis, we can just look in the y-axis and we can sum all the forces, which is just tension minus the force of gravity, is equal to mass times acceleration in the y direction. Okay, so we eliminate the pulley from consideration by assuming its mass to be negligible compared with the masses of the two blocks. So with some algebra, you just end up with this equation, which is the tension minus the weight is equal to the opposite of mass times acceleration. Okay. So what does that give us? Well, I want to take this equation and solve for a, because what we're trying to do is find the acceleration. All right, so if we do that, we have the acceleration is equal to little m over big M plus little m times gravity. That's equal to 2.1 kilograms divided by 3.3 kilograms times 9.8 meters a second squared. Okay, and then the numeric value for that is 3.8 meters a second squared. So I took this equation and I wanted to get rid of t because t isn't helpful to us if we're not trying to find what it is. Now again, t is the same for both sides. So what I did was I took this equation which we found from the y components and I plugged in what we found for the x component up here, so big M times a. So I took this, plugged into that equation, and then I simplified, rearranged to solve for a, and that's what we get. All right, so this gives us our acceleration. Now I also wanted to find the tension. So to find the tension, at this point, I can really use any of the equations that we had before to solve for the tension. And our simplest equation happens to be this one. All right, so I'm just going to take that equation. T is equal to, oops, it's big M times the acceleration. And I found the acceleration, so this is pretty easy to find. All right, so you're just going to say that is equal to 3.3 kilograms multiplied by 3.8 meters a second squared, and you get something around 13 newtons for the tension. All right, well, there's another way that we can solve this that might simplify it a little better. And situations that we have with pulleys and blocks, you're going to see them a lot, and I have a method that might actually make it a little bit easier for us. So let's go ahead and look at the same situation we had before, but this time I want to simplify it by stretching out the string and keeping it in one dimension so that the acceleration kind of makes sense, so that acceleration is going in one direction. All right, so here's what I'm going to do. All right, so we currently have this block and this pulley. Well, what I can do is just bring this and slide it up here and then rotate all of the other forces with it so that it's in one linear fashion. All right, so what I end up with is big M with a chord between it and then little m mass over here. Now, if you draw in our forces, or do free body diagrams for each block again, you see that this is going to be a normal force, so this doesn't change at all. This is going to be the force of gravity, and you have a tension along the string. Well, you also have a tension along the string going that way. You have, and then in this direction, you have the force of gravity. Okay, which is different. So this is force of gravity of H, this is force of gravity of the block S. All right, and then you know that it's accelerating in this direction. So there's our acceleration. Okay, well, since it's accelerating in this horizontal direction, we don't need to worry about anything in the vertical direction. So don't need to worry about that, we don't need to worry about that. All we're concerned with is stuff happening in the horizontal direction. Well, if you notice that we have one t to the right and one t to the left, so those are going to cancel out as well. So this is going to cancel out, and that's going to cancel out. So the only thing we have left in this horizontal direction is the force of gravity. All right, we take that, we plug it into our kinematic equation. All right, or excuse me, our force equation, Newton's second law. All right, oops. All right, so F is equal to ma. Again, this is the summation of forces, and we're just going to do all the summation, or all the forces along the horizontal axis. We only have Fg, so this is going to be Fg of H. Oops, and that's equal to mass times the acceleration. Okay. Now, something we need to keep in mind is this is going to be, since we did all the forces of this entire system, this is going to be the total mass, all right? So this mass here is actually big M plus little m. All right, so if I write this out, we have mg, which is just little m times the gravity for there. That's the only force we have. And this is equal to, well, this mass is big M plus little m times the acceleration. And since we're trying to solve for acceleration, we find it the same way, which is little mg over big M plus little m. Now if we go back a slide and look at, so this compared to this, we have the same thing, right? So we got the same result, and we're going to get the same answer. Now to find the tension, again, we can do the same thing. We can either look at, but we need to look at blocks individually. So we can look at this left block individually or this right block individually. And it's going to be easier if we look at this left block because there's only one force acting on it. So if we sum the forces of this left block on the left side, set that equal to MA. So this is, in this case, we're looking at a block specifically, so we need to use just that one block's mass, which is big M times the acceleration, which we found down here. And that's the same equation that we had using the other method. I think this method is a little bit easier when you look at the situation as a whole instead of looking at things individually, because the tensions cancel out anyway, right? I mean, you have one going to the left, one going to the right. They're always going to cancel out. So I think it's easier if you break it up and you think of it as a system, and then if you need to find the tension later, you can go back and look at each block individually. Okay. Next example. So in the figure, a cord pulls on a box of sea biscuits up a frictionless plane inclined at 30 degrees. So we have our box here. The cord is pulling up and to the right at a tension of 25 newtons. The mass of the block is 5 kilograms. The force on the block's cord is 25 newtons. What is the box's acceleration component along the inclined plane? All right, so we need to find where is it accelerating. Is it accelerating in this direction or in this direction? We're not sure. All right, or it might not be accelerating at all. We want to see what happens. All right, so for convenience, we draw a coordinate system and a free body diagram as shown in this figure. The positive direction of the x-axis is going to be up the plane. All right, so we just made our kind of change in coordinate axes here. We said that x is going to be up across the plane, and y is just going to be in that direction. And of course, you have the force of gravity pulling straight down. Force of gravity is always straight down. Okay, so the force from the cord is up the plane, has a magnitude 25 newtons. The gravitational force is downward and has a magnitude of mg, which is 49 newtons. So this is, again, force of gravity is always just mg. So also the component along the plane is down the plane and has a magnitude of mg sine theta. All right, so if we look at this picture here, what we only really care about is this part here, because that's what's going along the plane itself. And we expect the object to be accelerating along that plane. So we don't really care about this vector here, which is just going to cancel out with a normal force anyway. All right, so to get this, we use mg sine theta. Now, we need to be careful. We are using the x direction here, but because of how these angles are set up, we want to keep theta the same. It's going to be mg sine theta, not mg cosine theta. Okay. So to indicate direction, we're going to put a negative sign in front of our mg sine theta, right? Because it's going to the left on this plane. So we have this mg sine theta, and we'll call it negative since it's going away from positive. Okay. So we want to use Newton's second law, which is summation of forces is equal to ma. We'll just use the x there to denote we're talking about just in the x direction. All right, we're going to sum all of our forces up, so it's just going to be t, which is in the positive, and then minus mg sine theta, which is in the negative direction, and that is going to be equal to mass times the acceleration of the object. All right, so to find the acceleration, we simply just rearrange this equation to solve for a. So it's t minus mg sine theta divided by m. All right, now plugging everything in, we have 25 newtons minus 5 kilograms times g, which is 9.8 meters a second squared. Remember, g is 9.8 meters a second squared. It's not negative 9.8. So anytime we have just the variable g, or excuse me, the constant g, it's just 9.8. Don't put an extra negative sign in there. We've already accounted for that. Okay, and then we have sine 30 over here. Now we're going to divide this all by the mass again, which is 5 kilograms. Okay, so plugging this in, we get 0.100 meters a second squared. And since we get a positive value, we can assume that the acceleration is in the positive direction. So it's actually getting pulled up, and it's not getting dragged down. So we can get rid of our negative. Okay. Let's move on to our last example. So in the figure, a passenger of mass m is equal to 72.2 kilograms stands on a platform scale in an elevator cab. Now we're concerned with the scale readings here when the cab is stationary and when it's moving up or down. All right, so we can see we drew our free body diagram. We have a normal force going up. You have the force of gravity pulling down. Now, if this elevator was accelerating at all, you would have either an acceleration up or down, depending on where it was accelerating. Okay, so find a general solution for the scale reading whatever the vertical motion of the cab. All right, so the reading is going to be equal to the magnitude of the normal force on the passenger from the scale, right? So the normal force is the force that's going to be pushing up on the scale, which is going to give it its reading. Now, we can use Newton's second law only in an inertial frame. If the cab accelerates, then it is not an inertial frame. So we choose the ground to be our inertial frame, and then we make any measure of the passenger's acceleration relative to it. All right, so we're doing all of our measurements as if we were observing this from the ground. Okay, so because the two forces on the passenger and his acceleration are all directed vertically along the y-axis, we can use Newton's second law for the y components. Doing so, we sum all the forces. We have the normal force minus the force of gravity, right? Normal force is up, gravity is down, and then that's equal to mass times acceleration. Now, solving for this for the normal force, we just add force of gravity to both sides. You can see that the normal force is directly related to the acceleration of the object, or of the elevator, rather. Okay, so now just substituting in mg, we find this general equation for the normal force. Okay, so no matter what the situation is, this is going to be the reading on the scale. All right. Okay, so continuing on, what does the scale read if the cab is stationary or moving upward at a constant 0.5 meters a second? So it's either stationary or it's moving at a constant speed, which means there's no acceleration, right? If it's either stationary or moving, as long as it's not accelerating, there's no as long as there's no change in speed, there's not going to be any acceleration. All right, so substituting this and other known values into the equation, we find that our normal force is going to be equal to, right, the equation that we're given, that we found before. And this is going to be 72.2 kilograms times our acceleration due to gravity, which is 9.8 meters a second squared, plus 0, because there's no additional acceleration. Okay, so plugging that in, we get 708 newtons. So what does the scale read if the cab accelerates upward at 3.2 meters a second squared, or downward at 3.2 meters a second squared? All right, so let's look at our case upward first. So the normal force, and using the same equation that we had before, 72.2 kilograms times 9.8 meters a second squared plus 3.2 meters a second squared. And in this case, we get 939 newtons. Oops. 939 newtons. All right. So the normal force, if it was going downward, is the same equation, but now we have a negative, now we have a negative 3.2 meters a second squared. and that gets us 477 newtons. So the reading on the scale is actually going to change. If he's accelerating upward, the reading on the scale is actually going to increase. If he's accelerating downwards, the reading on the scale is actually going to decrease, or he's going to lose weight. Okay, so during the upward acceleration in part C, what is the magnitude F net of the net forces on the passenger? Well, the net force is just going to be the normal force minus his weight, which is mg, right? So if he's accelerating upward, normal force is 939 newtons, and his weight is 708 newtons. Right? So the net force on him is just going to be equal to 231 newtons. So since there's a net force on him, we know that he's going to be accelerating. All right, that's it for the example problems for this chapter. Next chapter, we're going to continue on with forces, and this time we're going to include friction as well. All right, thank you.